In the context of econometric theory, Python can be used to illustrate the theory numerically. In addition, we can derive expressions using symbolic calculations. We start with NumPy. To work with NumPy, we have to use an import statement. I'm using Spider as my integrated development environment. I personally like Spider because you can see the structure of data without using print functions. So I state import NumPy as NP. In this case, we assign an acronym NP, which is very common. For instance, we can assign values to two different variables. Then we print the square root of one of the variables. So we assign 7 to A and 2 to B and take the square root. The function sqrt requires the prefix NP, so we use NP and then the dot operator. NP is needed so that Python knows where to search for the square root function. Inside the brackets, we state the argument of the function. So in our case, it's our object A, which has the value 7. Then we use the print function to display the result. To work with a data matrix, we need to introduce NumPy arrays. Arrays are used to store data. For instance, we can create column vectors, such as the all1 vector, which we need to obtain the constant term in our linear regression model. In this case, we call this all1 vector once, and we use the once function. Again, we point to NumPy using NP followed by the dot operator. And in brackets, we specify the dimension. And now you see you get an array and you have 5 entries. You notice that Python starts counting from 0. Using indexing, we can refer to each entry in an array. Again, don't forget Python starts counting from 0. We can use indexing as well to change the values of entries. So for instance, we can assign new values to our all ones vector. So here, for instance, I change the first entry, so it refers to 0, starts counting from 0. I change it to 3. And when we look at my array, I now have a new entry here at position 0, which is now 3. -1 is quite useful sometimes. -1 refers to the last entry. So I don't have to know the dimension of my vector. I can just refer to -1 to go to the last position. If I say -2, it goes to the one before the last one, and so on. We will play around indexing quite frequently, so we will come across a few nice ways to slice and dice our arrays. And you see now the last entry is changed to an 8. Notice that we use rectangular brackets to do the indexing. Now this is different from the round ones. The round ones are used in functions or methods, and we will come across them quite a few times. So don't worry about these terms. They always keep popping up. After a while you get used to it. We can also assign values all in one go when we start a new object. And we also provide the structure of the array. Now structure means, just like in the case of a matrix, we want to specify dimensions, so the number of rows, the number of columns. Let's look at an example. So here is our vector A. We use now the NumPy array function. And you notice we have these round brackets. We need that because it's a function. And we specify as an argument, in fact, a Python list. And this list, it looks like a list, actually positions these values into an array, starting with 1, 2, and so on. And now we obtain the array. and it's structured as a column vector. Next, we create an all-zero matrix of a certain dimension. Note that the first integer refers to the number of rows, whereas the second integer determines the number of columns. It's just like in matrix notation. Again, we can change entries using indexing. And as we have seen before, indexing requires rectangular brackets. So here we call this the matrix matrix. It's not a very exciting name. We use NP zeros, and now we provide what you call a tuple, which provides the structure of this matrix. So again, the first one is the number of rows, the second one the number of columns. Let's have a little look. 3 rows and 4 columns. Again, notice counting starts from 0. And then we can change one of these entries by using indexing. So rectangular brackets, 0 refers to the first row, 1 refers to the second column. So it would change my entry here. And you see now this entry is updated to 22. We can obtain access to the shape and size attributes. Attributes are very useful to store information on objects, and we will use attributes quite a lot once we go more into object-oriented programming. Now we have a look at shape and size in action. So here we go. I just use a print function. I refer to the object, which is the matrix object. You obtain a tuple with entries 3 and 4. The first entry, which would be position 0, is the number of rows. The second entry, which is position 1, is the number of columns. So for instance, if I put 0 here, that should give me the number of rows, which is 3. If I put 1 here using indexing, I should get the number 4, the number of columns. Let's have a look at size. Size gives you the number of all the different entries. This can be quite useful. So for instance, if you do some matrix manipulation and you need a matching matrix of a certain size, you can use the shape attribute to obtain exactly the dimension you want. Now let's create a suitable column vector and then conduct a matrix multiplication. I create an all-one vector, again I call it the ones, which refers to my ones function. I provide the structure, in this case 1 row, and the number of columns refers to the number of rows of my matrix. So now this is the all-one vector, and you see it's a row vector. And finally we multiply the all-ones row vector and the matrix using the matmul function. And so that would be our combined matrix after multiplication. Finally, it is quite useful to know how to create an identity matrix. That is a matrix with all 0 entries except on the main diagonal, which contains ones. Multiplying any matrix with an identity matrix, assuming suitable dimensions, results in the initial matrix. So nothing is really changing. The identity matrix is the neutral element in the context of matrix multiplication. So that's the function for the identity matrix. It's EYE and then the dimension. So that's our identity matrix. And you see on the main diagonal, it's all 1 and all the other entries are 0. Now let's build a data matrix. We start, for instance, with 3 explanatory variables and 2 observations. Hence, the matrix has dimension 2 times 3. We use the NP array function, and now you see things are getting a little bit more complicated. We have the first rectangular brackets, and then we have a second set. So matrix A has now this structure. You see the first 1, 2, 3 appears in the first row, and so the comma introduces the second row, 3, 6, 8, and that's the structure. So using that, we can fill data into a data matrix. So once we have this matrix, we can use it for further calculations. Now it's quite common that after an initial round of observations, you might update your data set, you might append your data set with additional observations. So for instance, we might have 3 additional observations to add. We can do that using a so-called vertical stack operation. So here is my matrix B, which adds 3 more observations. So now we have again 3 columns. So we have the 3 explanatory variables, and we have 3 rows. So these are additional observations. And what I want to do is I want to take this matrix A and the matrix B, and we want to combine them together. Now how to do this? Well, they refer to the same variables. So the columns should be the same. We just have to add these rows here to the first matrix using a so-called vertical stack. So we have to stack them vertically. And this is done using the NPV stack. And here we refer to the first matrix and then we add the second one. And let me just run this and you see the structure. And we call this now the data matrix X. So here we go. We have now in total 5 observations. Again, you notice we start counting from 0. To obtain a constant term, we require an all-one vector in our data matrix. Using the shape attribute, which we just saw in action before, it is easy to generate an appropriate column vector. Finally, the horizontal stack operation adds the all-one vector to our data matrix. So here we go, we generate a new all-one vector. In this case, we specify the shape based on how many rows we need. Well, we need the number of rows which we already have in our data matrix, which refers to 5 observations. So we use the shape attribute and take the first entry of the resulting tuple, which is the number of rows, and we have 1 column. We get our all ones vector or array, and it has exactly 5 entries, and now we have to take this array and our data matrix and stack them together, but this time horizontally. For that to happen, we use the mph_stack function, and you see here we reassign the X, the data matrix, to the new structure. So we start with the old one on the right hand side and reassign it to the new data matrix. That works perfectly fine in Python. So here we go, and now we have our all-one vector included into our data matrix, and now we could start running some further operations. So that's all for this session. I see you in the next one.